to my another video for visually impaired students on topic thermodynamics. Second law of thermodynamics. Need for the second law of thermodynamics. First law of thermodynamics is merely the law of conservation of energy. There are several phenomena which cannot be explained by the first law. The first law is not sufficient and has certain limitations which are discussed as follows. First law does not put out restrictions on the direction of flow of heat. The first law establishes the relationship between the heat absorbed and the work done by the system. It places no restrictions on the source of the heat or the direction of its flow. According to the first law of thermodynamics, it is possible to heat water using ice without any external effort. Yet we know from experience that such as a transfer of heat from lower temperature to higher temperature will not take place spontaneously. Heat is always found to flow from hotter to colder body. Thus, first law is unable to take the direction of flow of heat. It only indicates that if such process occurs, then the heat gained will be exactly equal to the heat lost. Similarly, first law cannot predict whether a gas can diffuses from lower pressure to higher pressure or water can flow uphill on its own or not. This first law provides no information regarding the feasibility of process. The second law of thermodynamics helps us to determine the direction in which the energy can be transferred. First law has no criterion for the spontaneity of a process. There are several natural processes which takes place there in their own direction only, but they proceed in reverse direction on their own. For example, water flows down the hill cannot flow up the hill its own. Flow of heat from warmer to colder body, expansion of gas into a vacuum, burning of fuels, etc. are some examples of processes which takes place only in the particular direction. Such as processes are like spontaneous process. According to the first law, it was suggested that decreases of heat content is the reason for a reaction in which the heat absorbed must be non-spontaneous. But there are some processes in which value is positive, then the reaction proceeds spontaneously, such as vaporization of water at low pressure. Hence, the del U cannot be the criteria for the spontaneity. Similarly, del H cannot be used for the predicting spontaneity because there are many reactions in which proceed spontaneously with a positive value of del H. For example, dissociation of ammonium chloride in water. Thus, it is seen that function U and H from derived from the first law of thermodynamics cannot predict the spontaneity of the reactions. Hence, there is need for the second law. It is the second law of thermodynamics which defines a new state function called entropy. Thus, function entropy along with other functions like free energy G is used to predict whether a given process is spontaneous or non-spontaneous. As stated by first law, the exact equivalence between the heat and the work is not possible. First law establishes the relationship between the heat absorbed and the work done by the system. According to the first law, when heat is converted into work, the work done is equivalent to the heat absorbed. While it is seen from experience that work can be completely transformed into heat, but heat absorbed cannot be completely converted into work without leaving some change in system or surroundings. The observations cannot be explained by the first law. The second law helps us to calculate the maximum fraction of heat that can be converted into work for a given process. Thus, the first law of thermodynamics is not sufficient, and therefore an additional law which explains the above limitation is necessary. Before taking up the various statements of second law of thermodynamics, We discuss what is cyclic process and Carnot cycle. Various statements of second law of thermodynamics can be easily understood. Cyclic process. In a cyclic process, a system after undergoing a series of changes returns to the original states as shown in figure 1. A system undergoes change from state A to state B by path 1 and returns to original states by path 2. This is a cyclic process. The net change of internal energy in cyclic process is zero, that is del U is equal to 0. Therefore, according to the first law, del U is equal to Q plus W. For a cyclic process, del U is 0, so equal to Q plus W. यहाँ से Q की वैल्यू नेगेटिव W आ गई. When the cyclic process is carried out at the constant temperature, the cycle is said to be an isothermal cycle. If the process is carried out infinitesimally small steps, the cycle is said to be reversible cycle. All through the reversible process is only imaginary and cannot be brought into practice, but the concept is quite useful in deriving some important relationship. The most well-known as cyclic process is Carnot cycle. The Carnot cycle was named after French engineer Sadi Carnot. He was interested in the efficiency of steam engine and other heat engines, the device which converts heat into work. He observed that the maximum conversion of heat into work is possible in a cyclic process in which all the necessary steps are carried out reversibly. Such a reversible cycle is Carnot cycle, and an engine operating on this basis of the hypothetical cycle is called Carnot engine. An expression for the efficiency of a Carnot engine may be derived using a schematic diagram as shown in figure 2. The system consists of a 1 mole of an ideal gas filled in a cylinder which is insulated and fitted with the frictionless piston. The gas is brought in contact with two heat reservoirs, source at temperature T2 and sink at T1, which are mentioned at the constant temperatures, where T2 is larger than T1. The Carnot cycle involves 4 reversible steps are shown in figure 2. Isothermal expansion, adiabatic expansion, isothermal compression, and number 4 adiabatic compression. The process is represented on the pressure volume diagram in figure 3. Step 1. Isothermal reversible expansion. The cylindrical containing 1 mole of ideal gas having volume V1 is placed on the source. The gas absorbs quantity of heat Q2 and undergoes isothermal reversible expansion to the volume V2 indicated by the curve AB. The work done W1 by the system is given by negative W1 is equal to RT2 ln V2 divided by V1. As in isothermal process, del U is equal to 0. The work done is equal to the heat absorbed Q2, so that negative W1 Q2 RT2 ln V2 divided by V1. Work done by the system is taken as negative according to the IUPAC convention. Step 2. Adiabatic expansion. The cylinder is removed from the source and kept on insulating base. The gas is allowed to expand adiabatically from volume V2 to V3. In this step, the temperature decreases to T1. This path is shown by the curve BC. In figure 3, the heat is absorbed by the system is 0. Expansion takes place under the adiabatic condition. The work done W2 is given by this equation. Cv is the heat capacity of ideal gases. Work done is negative by the usual conventions. Isothermal compression. This path is shown along the curve CD in figure 3. In this step, the cylinder is removed from the insulating base and is kept in contact with the sink at temperature T1. The gas is compressed isothermally till the volume decreases from V3 to V4. The work done on the system is positive by the convention and is given by the work W3 is equal to RT1 ln V4 by V3. An amount of heat Q1 exactly equal to the W3 will be returned to the sink. Thus we can write this fourth equation. Adiabatic compressions. In this step, the cylinder is removed from the sink and placed on the insulating base. The gas is compressed adiabatically along the curve dA. The volume reduces from V4 to V1 and the temperature of the gas rises from T1 to T2. The work done is positive by the convention and given by the equation 5. As a result of these four operations, the system returns to its original state and the reversible cycle is completed. The total work done W is the cycle is given by equation 6. Net heat absorbed Q is given by this equation. Since the point T2, V2 and T1, V3 lies on the same adiabatic curve, BC and T2, T1, T4 lies on the adiabatic curve AD. Then using these expressions, TV gamma minus 1 is equal to constant. Comparing equations 7 and 8, we get V4 divided by V3 is equal to V1 divided by V2. Substituting these equations, we get the value of W, equation 11. From the above derivations, it is observed that the work done in Carnot cycle is only the work involved in the isothermal operations, because the work done in adiabatic operations cancelled one another. Efficiency of Carnot cycle and the Carnot theorem. The efficiency neta of the Carnot cycle or the heat engine is defined as the ratio of the work done by the system to the amount of heat absorbed at the higher temperature. Thus, neta is equal to W divided by Q2. Substituting the value of W and Q2 from equations 11 and 12 respectively. Here, neta value T2 minus T1 divided by T2. Equation 13. From the equation 13, it is clear that the efficiency of the reversible heat engine depends only upon the temperature of the source and the sink, and is independent of the nature of the working substance. In other words, the old reversible heat engines working between the same two operations, same two temperatures, having the same efficiency. Also, the efficiency of a reversible heat engine is maximum for the given temperature. This is called Carnot theorem. Thus, the efficiency of heat engine operating in Carnot cycle depends only on two temperature at which the engine operates. The greater the difference between T2 and T1, greater is the efficiency. For a cyclic process, net heat absorbed is equal to net work done. So Q2 minus Q1 is equal to W. Here neta is equal to Q2 minus Q1 divided by Q2. The two important conclusion arises from the equation 15. If T1 is equal to T2, then no work is done in the Carnot cycle. There is more clear from equation 10. When T1 is equal to T2, then the work done is in isothermal expansion. At temperature T2 will cancel out the work done by the system in isothermal expansion at temperature T1. In other words, in Carnot cycle, no heat will be converted into work if only isothermal expansion and the compression above are carried out. It follows from equation 15 that efficiency neta of the Carnot cycle will be unity. If T1 is equal to 0, and as T1 can never be 0, therefore T2 minus T1 divided by T2 is always then unity. Hence, the efficiency of a heat engine is always then unity, less than unity. Thus, only a fraction of the heat absorbed at higher temperature can be converted into work. Statement of the second law of thermodynamics. Having discussed the cyclic process of the heat engine. We can now give the statement of this second law, which can be easily understood from the efficiency of a Carnot cycle. Kelvin statement: since T2 minus T1 divided by T2 is less than 1, it shows that the W is less than Q2, that is, the work done is less than the heat absorbed. This means that only a part of the heat absorbed by the system at the higher temperature T2 is converted into work. The rest of the heat Q1 is given out by the system to the surrounding when it is at lower temperature T1. Based on these observations, Kelvin stated the second law of the thermodynamics as follows: it is impossible to use a cyclic process to transfer heat from a reservoir and convert it into work without at the same time transferring it from hotter to colder body. It can also be stated as it is impossible to convert heat completely into work without leaving some effects in the systems or surroundings. All through the second law has been stated in a number of ways, but all these statements have the same fundamental concept, that is, work can always be converted into heat, but the conversion of heat into work does not take place under all conditions. Kelvin and Planck's statement: we have seen that the work done by a heat engine operating in a cycle is zero when the two temperatures are same. The Kelvin-Planck statement of second law is: it is impossible for a system operating in a cycle and connected to a single heat reservoir to produce a positive amount of work in the surroundings. In other words, it is impossible to construct a perpetual machines which operates solely by removal of heat from a thermal reservoir. Clausius statements: a heat engine operating in a cycle can perform work only by absorbing heat from a reservoir. Work at a higher temperature and by the rejecting the difference between the heat absorbed and the work done by the engine to another reservoir at a low temperature. On this fact, the Clausius statement of second law is based. Clausius statement of second law of thermodynamics is: it is impossible to construct a machine that is able to transfer heat by cyclic process from colder to hotter body without use of any external energy. Is this? ये इसके सम एग्जांपल्स हैं, ये आप ट्राई कीजिएगा. Thermodynamic scale of temperature. We are familiar with the construction of most commonly used thermometer containing mercury sealed in a glass bulb connecting to a capillary tube. On this tube, O is read as the length of mercury column when in the contact with the ice, 100 corresponding to the length of mercury column in boiling water. The length of mercury column between 0 to 100 is divided into 100 equal divisions. Each division is equal to the 1 degree Celsius. This is Celsius scale of temperature. As this scale is based on the coefficient of expansion of a liquid, therefore using the different liquids in the thermometer will show the different value of temperature for the same object. This is problem is got solved by the study of properties of gases. It was found that an ideal gas cases to the exist at a temperature of minus 273.15 degrees Celsius. This temperature was called absolute zero temperature. The temperature scale suggested on this basis is called ideal gas temperature scale and is found to be independent of the nature of gases. Lord Kelvin developed a thermodynamic scale of temperature based on the fact that the efficiency of the reversible heat engine is independent of the nature of gas taken in the heat engine. This scale is found to be identical with the ideal gas temperature scale. Consider a reversible heat engine operating between two constant temperature heat reservoirs. One of the reservoirs acts as a source and the other acts as a sink. The temperature of each reservoir on the new scale may be taken as the proportional to the quantity of the heat absorbed Q2 from the source of heat lost Q1 to sink. Let theta 1 and theta 2 represents the temperature of the sink and source respectively. Then on the thermodynamic scale we can write the equation 1. The equation 1 gives the ratio of two temperatures based on the quantities of heat exchanged and is independent of the nature of thermometer substance. Taking the reciprocals of the equation 1 becomes this. Subtracting from unity we have the value of W divided by Q2 is equal to theta 2 minus theta 1 divided by theta 2. This equation defines that the efficiency of the reversible heat engine in terms of Kelvin temperature. Q2 minus Q1 divided by Q2 is equal to W divided by Q2 is equal to unity. Therefore, the 0 on the Kelvin scale is the temperature of the sink of the reversible heat engine having efficiency equal to 1, which means that such a cycle is completely converts into heat into work. This is possible only if the lower temperature theta 1 is equal to the absolute 0 on the ideal gas temperature scale. In fact, the ideal gas scale and Kelvin scale are identical provided the gas is ideal. The temperature on the thermodynamic scale can be expressed in terms of degree Kelvins represented as K. Further, it has been found that if theta 1 is taken equal to the 273.16 Kelvin, the triple point of water, then the Kelvin and the Celsius scale becomes identical, that is 273.16 Kelvin is equal to 0 degree Celsius. Anotropy. The function anotropy was established from the work of Carnot. Celsius in 1850 introduced this function of state S. For a reversible Carnot cycle operating between temperatures T2 and T1, the efficiency is given as neta is equal to Q2 minus Q1 divided by Q2 is equal to T2 minus T1 divided by T2 equation 1, where Q2 is the heat absorbed isothermally at temperature T2 and Q1 is the heat lost isothermally at temperature T1. Rewriting this equation 1, we get the equation number 2. In general form of equation 2 may be written as Q reversible divided by T is equal to constant, where Q reversible is the amount of heat exchanged in a reversible process. Thus we can say that the heat absorbed or lost isothermally and reversibly divided by the absolute temperature at which the heat is exchanged is a constant quantity for a given system. Equation 2 has been derived by taking positive sign of the heat absorbed Q2 and the negative sign of the heat lost Q1. If Q2 is heat absorbed and Q1 is heat evolved, then we can write these equations. Therefore, Q is not a state function, is the summation Q divided by T is equal to 0, or when the isothermal and adiabatic process in a Carnot cycle are carried out in infinitesimally small steps, the summations of the Q divided by T terms is equal to 0. Anotropy is a state function. Consider a cyclic process A be carried out reversibly. It can be shown to consist of a number of small Carnot cycles as shown in figure 4. The horizontal lines represent the adiabatic process, while the slanting vertical lines represent the isothermal process. By making each Carnot cycle extremely small and in increasing their numbers, it can be made to correspond to the continuous curve ABA. Thus, reversible cycle can be considered as being made up of the infinite number of Carnot cycles. For each cycles, we have summation of q divided by t is equal to 0 when the changes are made in infinitesimally small amount of. We can write the equation for a cyclic process performed in two steps, that is from A to B and back B to A. We can write the equation number 5 और बाद में इसको इक्वेशन नंबर 5 से हमें मिलती है इक्वेशन नंबर 6. It follows that the q divided by t is definite quantity whose value depends only on the initial state A and the final state B and is independent of the path followed for the process. For a reversible process, we can write quantity q divided by t as q reversible divided by t. Thus, we conclude that quantity q reversible divided by t represents a state function. This state function is called entropy of a system and is represented by S. Thus, S is equal to q reversible divided by t. Entropy is an extensive variable and is defined only in the terms of differences. The change in the value of entropy is going from one state to another is independent of the path. Del S is equal to q reversible divided by t, where SA and SB are the entropy in states A and B of the system respectively. As entropy is a state function, a small change in its value can be represented by an exact differential del S. Hence, we can write del S is equal to q reversible divided by t. Unit of entropy. Entropy change is expressed as del S is equal to q reversible divided by t. Entropy is expressed in terms of joules per degree Kelvin. When heat is expressed in calorie, then entropy is reported as calorie per degree. Further, entropy is extensive property. It is therefore necessary to mention the amount of substance involved. Usually, it is expressed for 1 mole of substances. Hence the unit of the entropy are calories per degree moles. When heat is measured in joule, we can write the unit of entropy as joule per degree per mole. Entropy change in the reversible process. Consider a process taking the place under completely reversible condition, that is the system absorbed heat reversibly and the surroundings always transfer heat reversibly. Let q reversible be the heat absorbed reversibly by the system, then the heat is lost by the surrounding will also be the q reversible. If the heat transfer can takes place isothermally at the absolute temperature T1, then the entropy change in the reversible processes will be the negative of the entropy change of the surroundings. That is, del S of the system is negative del S of the surroundings. Entropy change of the system is given by del S of system is equal to q reversible divided by t. Entropy change of the surrounding is given by del S of surrounding is equal to negative of q reversible divided by t. The total entropy change of the combined system and surroundings will be equal to 0. Thus, the following conclusions can be drawn from the above discussions. Number 1. The total del S for the system and surroundings when reversible isothermal change occurs in it is 0. The total entropy change for a reversible isothermal cycle is 0. Entropy change in an irreversible process. If any part of a cyclic process is irreversible, the process as a whole becomes irreversible. Let Q irreversible be the heat lost by the surrounding. This amount of heat is absorbed by the system, but according to the definition, the entropy changes of the system depends only on the heat absorbed reversibly, that is Q reversible. Thus, the del S of system is equal to Q reversible divided by T. Further, assume that the surrounding flows Q irreversible amount of the heat isothermally in the infinitesimally small steps, then the anetropic changes of the surroundings will be del S of surrounding is equal to the negative of Q irreversible divided by T. The net change in the anetropy of a system and surrounding combined is given as by the equation 1. Further, we know that the work done is in reversible process is maximum. That is, first law of reversible process can be written as del U is equal to Q reversible minus W reversible. When saying the process is carried out irreversibly, can write the equation number 3. As the internal energy is a state function, del U is the same whether the process is carried out reversibly or irreversibly. From the equation 2 and 3, we get the equation number 4. Comparing equation 1 and 4, we can write as del S of system plus del S of surroundings is greater than 0. Thus, we conclude that in an irreversible process, the entropy of a system and the surroundings taken together always increases. All the process in nature occurs spontaneously, and all the spontaneous processes are thermodynamically irreversible. Thus, Celsius concludes that the entropy of the universe is increasing. The second law of thermodynamics may be stated as all the spontaneous processes are accompanied by a net increases of entropy. That is, the entropy of the universe is increasing continuously. The result of the entropy change in a reversible process and in the irreversible process may be written as form this equation 5 and 6. Combining these two expressions, del S of system plus del S of surroundings is greater than equal to 0, where equal to sign is represent reversible process and greater than signs represents the irreversible process. Celsius inequality, the total entropy change for the system and surrounding for an irreversible process is written as del S of system plus del S of surroundings is greater than 0. Here the equation number 7 in Q irreversible is the heat transferred from the surroundings at the temperature T. Then we get from equation 7 to equation 8 when the change in entropy is small. Above the equation can be written as equation number 9. Expression 8 and 9 are known as Celsius inequality. Celsius inequality assumes that the entire universe could be considered as isolated system in which the all naturally occurring processes are irreversible. On this basis, it is often stated that the energy of the universe is constant and the entropy of the universe always tends towards maximum. Physical significance of entropy. The physical significance of entropy lies in its ability to provide a measure of degree of disorder or randomness of a system. The greater is the randomness in a system, higher is the entropy. All spontaneous processes such as diffusion of gases, flow of water down the hill, flow of heat from hotter to colder, and are accompanied by increasing in the disorder of the system. The spontaneous processes are accompanied by increase of entropy as well as increase in the disorder of the system. It has been seen that melting of solid, vaporization of liquid are processes in which the disorder increases and hence entropy also increases. We know that a solid having a definite crystalline structure has lowest disorder and thus represents a state of lowest entropy. The order is less in liquids and least in gaseous state. Let us correlate anisotropic changes with the randomness by considering the anisotropic changes during phase transition. Anisotropic change during the phase transitions. Change in the physical process. It may be occur in the following process: a solid melts, or when a liquid freezes, a liquid vaporizes, or a gas condenses. A solid changes from crystalline form to another. Entropy of fusion or melting. When the solid changes into liquid state and its melting point, the process is called fusion. Heat is absorbed during the fusion. The entropy changes accompanying fusion is given by del S F is equal to del H divided by Tf. We heard del HF is the latent heat of fusion, Tf is the melting point of the solid. Entropy of vaporization. When substance changes from liquid to vapor state reversibly at its boiling point Tb under a constant pressure, the amount of heat absorbed is del Hv. Then the entropy changes accompanying the process is del Sv is equal to del Hv divided by Tb. It may be noted that both the process, that is fusion and evaporizations, are endothermic. Hence the del Hf and del Hv both are the positive, that is these processes are accompanied by increasing of entropy. On other hand, the change of state from vapor to liquid from liquid to solid involves evolution of heat and are negative. Hence, the processes of condensation, of vaporization, and freezing of liquid are accompanied by decreasing of entropy. Entropy of transitions. When one mole of a substance undergoes changes of state from the one crystalline form to another, the anisotropic change involved is known as the anisotropy of transition. If del H Tr is molar heat of transition of the substance and T is the transition temperature, then del Str transition is equal to heat of transition divided by T. As molar heat transition, del HTR may be heated, evolved, or the absorbed. Thus, the entropy of transition may be negative.